Okay, welcome back everybody. We'll continue on with the discussion on the various circuits in the 4CX250B tetrode amp. Again, what you're looking at here is the basic tetrode schematic with input circuit, parasitic chokes, a screen bleed, swamping resistor on the grid, and RF choke for the plate, and the output tank coil. This doesn't include the relays and routing for transmit and receive bypass, and of course you don't see the power supply on this schematic. Here is the complete schematic of the rig we're talking about. And what I'm going to try to cover today in this video is going to be the keying circuit right here with the two relays. I'm going to cover the voltage divider circuit, talk about how you can figure that out, and the swamping resistor, how to figure that out, and the math behind it. So we'll get on with the keying circuit. This is rather unique in that you have a problem with tetrode amps. Here's the large. You can see all of that. I can see most of it. We'll leave the power supply part out. What we're worried about right now is the main keying circuit. A tetrode amp, the high gain tube, like a tetrode is, can have some anomalies, and sometimes it's referred to as hot switching. It means that the screen cannot be activated too soon after the antenna relays are closed and the drive is given. If that happens too quick, like say all at once, you can have an arc occur at the antenna relay because the tube is so fast at going into conduction. So there's a little trick circuit that I come up with a long time ago, and it's really simple. It just requires a couple of resistors, a capacitor, and a diode. And we're talking about this resistor, this diode, and this capacitor. Really make this circuit work different. These cut sheets, by the way, are available. I'll put up my email address and just request the 4CX250B schematic sets, and you can get these and sit down and study them. Okay, when RF is applied at the radio input, it is sampled by a 10 puff cap and rectified by the two 1N 4148 diodes. This charges the 10 microfarad cap, and then it's fed through the 2.7K resistor to the base of the keying transistor. Out of the keying transistor, this goes two different directions. When this conducts, it pulls to ground. So one side of our relays are given the 28 volts, 25 volts. These are 24 volt relays. And so that would cause the relays to close. But there's a little timing thing that occurs in here. Okay, RY1 closes first because it is directly connected to the collector. But RY2 is delayed by the charging of the 220 capacitor, 220 microfarad capacitor. And the voltage drop across this 100 ohm resistor. That causes this one to close first. This is your antenna that connects the radio to the input, the grid of the tube, and the antenna connects to the tank, the pi output circuit of the tube. RY2 is the screen relay. This is why we want to delay it. We want to give time for the antenna. Pull this down here. We want to give time for this to close, and then on the opposite end of the amp, the same thing happens with the other half of this relay. The antenna gets connected to the pi output tank circuit. And it occurs so quick, just within milliseconds, but that's all it's needed. It just wants to make sure that the input and output relays are closed, and then the screen is allowed to come up to voltage and the tube can conduct. So there's no real time delay. It happens so quick you might be able to just catch that it's like a click click, that fast. Just click click. One is slightly follows the other. Then another thing that happens, there's a trick here going on. RY1 is delayed on the unkey by the charge held in this capacitor. And it's backfed by the 100 ohm resistor. The relay takes more current to close than it does to open. So when the relay is already closed, it doesn't take much to hold it closed for just a millisecond or so. So what happens, the antenna and radio stay connected. The relay holds closed, also the antenna on the pi tank. It allows the RY1 of the screen relay, it can unkey first because the diode blocks this charge from going back to the relay. So on the unkey, relay 1 or 2 unkeys first, and then RY1 unkeys. So it works backwards on the unkey. On the key up, relay 1 is delayed, or closest first, RY2 is delayed, and then on the unkey, RY2 unkeys first, then relay 1. Okay, like I say, if you want these sheets, just send me an email. I'll put it up at the end of the video, and you can have these to study. Okay, the next item we're going to talk about, how to figure out our grid swamping resistor. This is a resistor that eliminates the need for neutralization on these amps. They do not need to be neutralized because we swamp the input. We give it a good, like a dummy load really, so that no stray signal from the antenna or anything can get back into the grid circuit. It's swamped out. So it takes a fair amount of drive to drive this tube. And you have to figure this out between the amount of watts of drive that you have. Like you wouldn't want too low of a resistor if you only had a 2 or 3 watt radio. And to protect the tube from being overdriven and distortion, you want to make it heavy enough. So if you had, say, a 30 watt radio, you want to make this resistor small enough so that it dumps most of the power before it gets to the tube. Okay, here's how to figure that out. I'll show you with these resistor I'm talking about before we get into this so you have an idea. This is the plate compartment of the amp we're talking about, and this is the actual RF tube box. So we look underneath the tube, get it up where you can see it. It's this resistor right here, this 7 watt resistor, that dissipates the excess drive that the tube actually doesn't need. And you'll see it here, it's attached to the parasitic choke before it goes into the grid. So what we're going to talk about is how to figure out what the value of this resistor needs to be. If you want to look into the future, reach into my time machine here. If you were going to build a 3-tube unit, it would be the same thing. I haven't got the input coil mounted in this yet, so the 2 trimmers that would be connected to this aren't here, but I have the tubes wired in with the parasitic chokes, and here's our resistor again that we're going to be talking about, this resistor. In this rig, I've actually got a 619 ohm at 5 watt resistor in there. Okay, we'll get discussing that. Okay, you can get your calculator out. You might want to play with some numbers on this one. To find the grid swamping resistance for X number of drive watts, first take note of the RF voltage needed for the tube. In this case, most of the 4CX250 in class AB1 wants about 55 volts. Then you divide that across a chosen stock value of resistance, say 470 ohms. That will give you a value of current. Then multiply that number by 55 volts. Your answer will be the number of watts needed to give you 55 volts of RF, and it will be the wattage of the swamping resistor. Example, probably about 6.5 watts if you run that through the calculations. Alright, then if that number is higher than what you have for drive watts, then run the calculation again with a higher value of swamping resistance until you come out close to what you have for drive power. If that number is lower than what you have for drive watts, then run the calculation again with a lower value of swamping resistance. Here's the math behind that. E is the voltage that we have, say 55 volts, and we divide that across the resistance. That equation's Ohm's law, and it equals, when your answer is an amount of current. So 55 divided by 470 comes out to 117 milliamps. The next equation you run is E times I, voltage times the current. That equals power in watts. So 55 is the voltage times the current. It comes out to 6.435 watts. You see how that works out? So this is why I say you can run it for any value of wattage you want, and you'll come up with the resistor that you need for your swamping resistor. If you have any questions, do not be afraid to ask. I'm going to try to provide as much help as I can and guidance on anything that anybody might have a question with. Okay, now I got rid of my original schematic. Where'd it go? Come back here. Okay. On the original schematic, what we're going to talk about now is the divider resistors that basically some people might call dial-a-watt. It's how to figure out the current drop across the resistors and set up your screen voltage. Okay, here it is. On my amp, the one we're talking about, the little tube tester, it's set up like this. There's 6 resistors, there's 6 2.5K resistors tied in series. One end of them is tied to ground. The other end comes back and goes to the movable contact of the screen relay. And to figure out your voltage drop and what your wattage is, your current, you go 6 times the 2500 ohms. You get a total across the full stack of 15K in this case. And again, here we'd play a little math. E divided by R gives us current. So our voltage when we key up, is going to be 333, a little over 300, almost 334 volts, divided by 15,000 ohms, gives us about 26 milliamps. That's the actual number that I got on my calculator. Okay, we take the current times resistance equals the voltage. Now, the answer to this is going to be the voltage drop across each resistor. So here's the current divided by the 2,500 ohms. Each one of these resistors is 2.5K. So we get about 60, almost 65 volts across each resistor. So each one drops about 65 volts. All right, then how heavy do we have to make these resistors? Well, here's how to find that out. Current times voltage equals power. So we know our current because we figured that from the first drop across the stack. So we multiply that times 64. It comes out to almost 1.7 watts. The resistor you'd want in here, 2 watts, would be awful close. It would run pretty warm because this is going to be mounted in an environment that's probably warm already. So I would suggest probably a 3-watt resistor is about as close as you'd want to come. Now, if you have a screen voltage source that is higher than the 333 volts, say you've got 400, you can figure that out by what you need, because the tube only wants 350 max. So in that case, you could add a couple more resistors in here, and as long as all of them are the same, you then know what the voltage drop is across each resistor, and you can calculate that out. So in here, all the resistors are the same. Each resistor dissipates approximately 1.7 watts. I just happened to have 2,500 2.5K resistors. They were the square sand type resistor, and they were 5 watt. I just used what I happened to have. It's overkill, yeah, but it didn't hurt anything, and I already had them on hand. So that's the way that you can figure most of the stuff out. As long as your resistor will handle more power than you're asking it to dissipate, you're fine. Okay, let's see. I think that's about it. The next video, let me put my email up. Oh, that's too much shiny. Hold on. I thought that would be handy. Okay, we'll do it that way. Too much glossy. Next video, we'll talk about the input tuning network. How to figure it out, tune it up, and I'll give you some guidelines as to the starting diameter and how many turns. I may have that stacked over here. Maybe not. Do I not? Oh, I do. Okay, I've got to mount this on a little. See, there's the dropping resistor and the coil. These are 2 little ceramic, they call them pinch caps or pinch trimmers. The screwdriver adjust from the outside. Move that up there where you can see that. So the next video will be discussing how to figure this out and how to get SWR set. So hopefully we're moving right along here, and it can, some of you can start putting parts together out there. I know that's what you're waiting for. Okay. Alright guys, please remember, keep this going and enough interest. Please hit the like button for me if you would. It'll help draw more people in here. If you want to send me an email and get any of those schematics, just ask for the 4CX250B schematic sets. I'm up to about 13 JPEGs. They're all in JPEGs and they're all under 200K, so they won't take up a whole lot of room in your mailbox. Alright, thank you. See you on the next video. Thanks for watching. Bye.